Okay, so in this video I'm going to be recording solutions for the 2021 VCAA Exam 1. It's been quite a while since I've recorded a set of solutions, so please bear with me. Might not be as smooth as some of the previous ones. Okay, so we're going to work through this paper. It's an exam 1, so tech-free, no use of CAS, no reference to notes other than the standard formula sheet. Actually, I might just pause while I get that open. Okay, so I've got the standard formula sheet open on the second tab here. So these are all the formulas that we have access to. The calculus formulas are quite useful and definitely worth checking if you're slightly unsure of anything when you're working through, particularly quotient rule and making sure that you're subtracting in the right direction. That's a common error. Product rule, if you're unsure, refer to it there. Similarly, all the calculus rules here. The probability rules are less helpful. These ones here are, should be pretty routine, but those are useful. These ones here are not very useful, and the statistics ones can be quite useful as well. So making sure that you're familiar with your formula sheet is always a good idea. Okay, so let's get started working through our solutions here. So question 1, as expected in an exam 1, is a straight differentiate. Often it's a product or quotient rule or chain rule in question 1, and this requires none of those. It's just a straight differentiation. So if you need to, you could go over to your formula sheet for the rules for differentiating e to the x. So calculus differentiating e to the x gives us ae to the ax. So we can utilise that if we need to here. So in this case, the a is the -3. And so we're simply going to get, when we differentiate, so derivative of y is called dy dx, good notation. The 2 is just going to stay there, that's not going to do anything, it's just a number times the function. And so the derivative of e to the -3x is -3e to the -3x, which means when we combine that -3 together with our 2, we get -6e to the -3x. I've recently marked some students having completed this paper, and a couple of students mistakenly tried to use the product rule, thinking, oh, it's 2 times e to the -3x. Now, if you really want to use the product rule for that, you can, but product rule is for when you have two functions multiplying together, x times e to the -3x, or sine x times e to the -3x, or x cubed times e to the -3x, but just a number doesn't require a product rule. If you were to use the product rule here, you would derivative of the first function, derivative of 2 is 0. So you would get 0 times, and you do nothing with the second function, plus you leave the first function as it is, which is your 2, and you differentiate the second function. So product rule still works if you've got a number times a function, but the whole point is it's not necessary because the derivative of a number is 0 and that whole bit doesn't matter anyway. So it's really just about this part here. Okay, so most people differentiated correctly, recognise no need for any special rule here. This is a 1-mark question, so you'll just get one answer mark for having that answer correct. It must be perfectly correct to earn that mark. Evaluate f dash at 4, where f of x equals x times the square root of 2x plus 1. Okay, so we obviously first need to find f dash x before we can then find f dash at 4. And we recognise here that we do have a product, x times the square root of 2x plus 1. I'm also going to, just to help me differentiate, think about this as being x times 2x plus 1 to the half, just for my derivative rules. So over to my formula sheet, 2x plus 1 to the half, I'm going to be utilising this rule here. Okay, in this case, a is 2 and b is 1 and n is a half. Okay, and so then we want to use that rule there. Okay, so our product rule says that we differentiate the first function, which derivative of x is just 1, and we leave the second function as it is. I'm going to write it back with the square root. Plus, we leave the first function as it is, which is x, and we differentiate the second function, which is going to require chain rule, but we actually have a formula sheet over here which executes the chain rule for us, but really it is just chain rule. So it is something to the power of a half, so that's going to be half times that something to the power of negative a half, and then we have to multiply by the derivative of the something, derivative of the inside, which in this case will be 2. A couple of my students missed that 2 at the end there. Alright, so let's just tidy this up a bit before we substitute into it. So that's just square root of 2x plus 1. In the second part here, the half and the 2 are cancelling each other out. I'm going to undo those because I hate having lots of things crossed out. It gets hard to read your solutions. Try to avoid that when you're working through your answers. It gets really hard to follow what you're doing if you're crossing a lot of things out along the way. Just do it. So half times 2, that becomes 1. We could ignore those. We've got x, and then we've got 2x plus 1 to the negative half, which means that's on the denominator. So it's x on square root of 2x plus 1. Okay, so that's our derivative. And then we want the derivative at 4. So we're going to substitute 4 into that, which means we get 8 plus 1, so it's going to be 9. Let's just do that all in the one step. So we're going to get square root of 9 plus 4 over the square root of 9. Now, a lot of students have trouble with this square root of 9, thinking that's going to be plus or minus 3. The square root of 9 is just 3. Okay, in the same way that when I write 5, I don't mean plus or minus 5, I just mean 5, positive 5. I would write negative 5 if I meant negative 5. So when you write root 9, it's just root 9. It is just 3. What students are getting confused with in that instance is if you're being asked to solve the equation x squared equals 9, when you take the square root, it is possible that if something squared is equal to 9, it's possible that that something is either positive square root of 9 or negative square root of 9, in which case the solution to that equation is plus or minus 3. But if we just write root 9, we just mean root 9, so just 3. Okay, so we get 3 plus 4 thirds, and 3 plus 4 thirds, 3 is the same as 9 thirds plus 4 thirds, and so that is 13, oh, sorry, that is 13 thirds. Okay, it's a 2-mark question. There would be 1 mark, and it would probably be awarded as a method. It would be for knowing that you need to use the product rule. So if you made a slight error somewhere in calculating your product rule, you might still have earned the method mark, and then there would be an answer for 13 on 3, which must be correct. There's no very few consequential marks in maths methods. That mark at the end there wouldn't be consequential on your derivative. The answer must be 13 on 3 to earn an answer mark. It must be exactly correct. The bit of leniency there would be in the fact that if this is awarded as a method and the method that we're looking for is that you knew that you needed to use the product rule, then we're not allocating the mark for you having executed the product rule correctly. We're allocating the mark for being able to see evidence that you knew that the product rule was required. And so therefore you can get that mark without getting a perfect product rule, and then you can potentially still get 1 out of 2, even if you haven't earned, even if you substituted correctly into your derivative, but therefore still have the wrong answer at the end. Okay, question 2. Let the derivative of f of x, f dash x, be x cubed plus x. Find f of x given that f of 1 equals 2. So this is a really standard question 2 in an exam 1. We recognise that f of x is found by anti-differentiating f dash x. So the antiderivative of the derivative will give us f of x. And so therefore we're looking to anti-differentiate x cubed plus x. Anti-differentiating, we add 1 to our power and divide by the new power. Add 1 to our power, divide by the new power, and we're going to have a plus c, and that's what the f of 1 equals 2 is, giving us a point so that we can find c. So f of 1 is going to be 1 on 4 plus 1 on 2 plus c, and that has to equal 2. So therefore 3/4 plus c is 2, and c is therefore 2 minus 3/4. 2 is 8/4, 8/4 minus 3/4 is 5/4. And so therefore, making sure that we actually answer the question, which is to find f of x is equal to x to the 4 on 4 plus x squared on 2 plus 5 on 4. It's really important that you put the whole thing back together to actually answer the question to earn that mark. So this would be, again, an answer mark. Must be perfectly correct for the final statement of what f of x is with no plus c in it. There would be a, now, I don't know whether it be a method or an answer, but it's going to be pretty much the same thing in this case, but a method for anti-differentiating. And in fact, maybe it would just be for understanding that you need to anti-differentiate this function, but it could also be for actually successfully anti-differentiating, in which case it's probably an answer mark. I suspect you'd earn that first mark if you didn't have the plus c. You've done the same level of work at that level, but you then wouldn't have gone on and therefore wouldn't have a complete and final function if you didn't omitted the plus c earlier on. Question 3. Consider the function g, domain all real numbers. G of x is 2 times sine of 2x. State the range of g. Okay, so the range in a sine function is to do with amplitude. So that's going to be about this. So we know it's a sine function. It's being dilated by half from the y-axis. That's the period change. So the period would be pi. And it's being dilated by 2 from the x-axis, so that's going to affect the amplitude. It's going to go between -2 and +2. And so therefore the range of g is going to be from -2 to 2. Period of g we just talked about. The period of g would be 2 pi divided by n, which in this case is 2 pi divided by 2. That's that dilation factor from the y-axis, and so therefore the period is pi. Solve 2 times sine of 2x equals √3 for x is an element of R. So this is telling me that I'm going to need a general solution. I'm looking for a solution for all the possible solutions. Okay. So first things first is to get the sine part of the function on its own. Sine of 2x is √3 on 2. Then I need to identify where in the unit circle my solutions are. So I'm going to need exact values here. So I'm going to draw my special triangle. Half an equilateral triangle of side length 2, which makes that a 60-degree angle there, which is pi on 3, sorry, it's hard to read, and pi on 6. And Pythagoras tells me that this is √3. So if sine is √3 on 2, √3 must be the opposite side, and 2 is the hypotenuse, and so therefore we must be talking about pi on 3. So my angles are all to do with pi on 3. Sine is positive, and I know that sine is positive in quadrants 1 and 2. So all of my solutions must be located here and here. So pi on 3 up from there, and pi on 3 up from there. And I want to be able to describe every single solution. So if I can describe this one solution here, that's pi on 3, but then if I add another 2 pi onto that, and add another 2 pi onto it, and take away a 2 pi, I'm going to get more solutions, okay? So there's a whole family of solutions that exist at pi on 3, plus multiples of 2 pi. Now, remember when we're coming out of the unit circle, we're getting solutions for 2x, okay? So 2x is going to be equal to, 2x is going to be equal to, so that first family of solutions are at pi on 3, but then at every multiple of 2 pi, or whole number multiple, that's important, integer multiple I should say, and we'll add that in a minute. And then there's another whole family of solutions that are located over here at 2 pi on 3, and we can add multiples of 2 pi to get to the rest of the solutions in that family, because we're wanting to describe all of the solutions. Okay, so our next family of solutions are at 2 pi on 3 plus multiples of 2 pi. Now I did qualify, it's really important, we're not adding on 3.6 lots of 2 pi, we must be adding on integer lots of 2 pi. And that factors in that we can also take away 2 pi, because an integer can be negative. So if n was -3, that would be subtracting 3 lots of 2 pi, okay, which would be another solution. All right, so there's our general solution for 2x, but we're trying to solve for x. So we're going to divide everything by 2, which means pi on 3 divided by 2 becomes pi on 6. 2 pi n divided by 2 just becomes pi n. 2 pi on 3 divided by 2 becomes pi on 3. 2 pi on n divided by 2 becomes pi n. And that is only still true as long as n is an integer. So n is an integer is a really important part of that solution. 3 marks is slightly generous here. I'm not sure exactly how they would have awarded the 3 marks. I gave 1 if students recognised that pi on 3 was the basic angle. Okay, so their solutions were to do with pi on 3. So I gave a mark there. And then you could either say, you get 1 for each family, but both have to include the n is an element of z, or 1 for each family, and you only get 3 out of 3 if you have the element of z, or whatever it might be. Okay, so the z must be there though. Without that, the solution's not correct. So that would definitely be part of the solution. So whilst I've just allocated the ticks at those 2 separate things, each of those includes the fact that n has to be an element of z. Okay, and on to question 4. Sketch the graph of y equals 1 minus 2 on x minus 2 on the axes below. Label asymptotes with their equations and axis intercepts with their coordinates. It's really important that VCAA always asks for points labelled with coordinates. It should be a habit of yours by now, and if it isn't, you need to be making it a habit. So let's think about this function. It's a hyperbola. I'll just thought there might be some space under there. It's okay, let's go here. So y equals, I'm going to think of it as this, negative 2 on x minus 2 plus 1. Okay, so the negative out the front there is the hyperbola reflected in the x-axis, which means it'll be in these two quadrants rather than the other two. Then it's been dilated by a factor of 2 from the x-axis. Okay, so that's just going to stretch it a bit. It's not going to change a lot about what I draw. We've translated to the right by 2 and up by 1. Now, if I was being asked to state the sequence of transformations, I would definitely write translation. I need to use that word. I wouldn't just write from x, I'd write from the x-axis, but that's me thinking in my head. I wouldn't be actually writing those things down if I was doing this myself. Okay, so the right by 2 and up by 1, they're my asymptotes. Okay, so I'm going to draw those in. I must say, as I said, I've just marked a set of exams of students having completed this exam, and lots of them didn't have straight asymptotes, especially this one. You know, they need to be straight. Bring a ruler in if you can't do it by hand roughly straight. There's nothing wrong. You're allowed to bring a ruler in, and you should bring a ruler in if you can't draw your asymptotes and your linear graphs as straight without it. So asymptotes labelled with equations. So this line has equation x equals 2. We've gone up by 1, so there's an asymptote at y equals 1. Again, I want to make sure it's straight. It should be a dashed line, not a solid line. Just emphasize straight, and then I didn't draw it very straight at the end there, because I was trying to draw from right to left. Still struggling. Use a pencil, rub it out, and fix it if it's not right. It's really important that your graphs are accurate and straight, and particularly in recent years they've started always giving you a grid when you have to draw a graph, and in some ways that's helpful, but it actually also sort of necessitates that you must almost be more precise. So when we work out our axis-intercepts, so if we do our y-intercept, we let x equal 0, so we're going to have y equals negative 2 on negative 2 plus 1, so it's going to be 1 plus 1, so it's going to be 2. So that's at 0, 2. I'll label that in a second. And then when I work at my x-intercept, I'm going to have 0 equals minus 2 on x plus 1 plus 1. So it's positive equals positive. Multiplying both sides by x plus 1, so we get 2 equals x plus 1, and subtracting 1. Oh, have I changed the function there? Sorry. Oh, I've copied the function out wrong. Sorry. It's x minus 2 on the denominator there. I'm sure you're all shouting at me. Alright, so there's an x minus 2, and so we add 2 to both sides and we get x equals 2. Sorry, x equals 4. Alright, so that's going to be here. So you've got to be careful about just sort of randomly drawing in a graph that does that, okay? Because, well, asymptotic behavior issue there, you'd lose your shape here, you don't actually go through the x-intercept there, but actually, because you've got a grid, it goes through a really defined set of points, and it should actually go through all of those points. So certainly in my head, I was thinking through, okay, well, when x equals 3, if I put 3 into that function, I've got 1 on the denominator, so it's negative 2 plus 1, so it's just negative 1. So I know it goes through 3, negative 1. So I'm just going to mark a dot there. It should actually go through that point. And it just helps to get the shape right. Same thing when x equals positive 1. 1 minus 2 is negative 1. 2 on negative 1 is negative 2, but there's a negative out front, so that's positive. And then plus 1. So it should go through 1, 3. We should be able to calculate some points. You might want to sub in a few other points. You know, if an x equals negative 2, then that's going to be... negative 2. So we're going to have negative 4 on the denominator there. So that's going to be negative to positive half. It's 1 plus a half. So it should actually be here at 1.5 there. Okay. So you want to think about some points. And you can actually use the symmetry of the shape. So it actually, at 6, I'll also be at half. You can work it out, but you should be able to use the sort of symmetry of what you've just worked out as well. But it should actually go through those points. It's really important that you kind of, when you've got a grid, you sort of think that through. You might want to put in a couple more points. You know, when x equals 4, you're going to have 4 minus 2 on the denominator, so that's 2. So again, it's going to be negative 1 plus 1, so that's 0. Oh, sorry, that's x. I was thinking when y equals 4. But say when x equals 1.5, you might sub in. But just sub in a few whole number values just to give you a couple more points so your shape is roughly right. You also shouldn't have had an issue with a number of students just sort of stopping their graph somewhere about here. Your graph needs to continue all the way to the edge of the axes. when you're drawing a graph with asymptotes, you need to make sure that your sketch reflects your understanding of what an asymptote is, that your graph approaches but never reaches the asymptote. The graph got a bit wobbly up there because I was drawing in the other direction. Let me try doing it this way. Draw it in a couple of parts if you need to. Draw it to that bit. Your graph needs to approach that asymptote. It needs to not get parallel to that asymptote. We needed to have axis intercepts labelled with coordinates, so I need to label that as 0, 2 in order to get full marks here. Okay, that didn't join very smoothly there. Let's try that again. That's more a screen resolution issue there. But hopefully when you've got your pen and paper, you'll be able to get those to join a bit more smoothly than mine did. But yeah, your graph needs to be quite precise. This x-intercept is for 0 because we need to label with coordinates. Okay, so you've got 3 marks here, and there are 2 specific things that are specified. Asymptotes labelled with equations. Okay, so you're going to have 1 mark for your asymptotes labelled with equations. You're going to have 1 mark for your axis intercepts labelled with coordinates. Okay, and then you're going to have a 3rd mark which will be for shape, and there'll always be a mark for shape. And if your graph sort of goes way off here, if your graph touches your asymptotes, if your graph gets parallel to your asymptotes out here and starts to do that, you're not going to get a shape mark. Okay, so it's really important that you take time, that you take care, use a pencil, fix it if it's wrong, and make sure that you've got 1 nice smooth line, or in the case of hyperbola, 2 nice smooth lines drawn to earn your shape mark. Okay, find the values of x for which 1 minus 2 on x minus 2 is bigger than or equal to 3. Okay, this is all the same question. We need to recognise that it's asking me when the graph I just drew up here is bigger than or equal to 3. So let me think about that. Okay, well here's 3 here. I want to know when the graph is bigger than, so not equal to. So I'm interested in this bit of the graph here. When the graph is, the function is, the y value is bigger than 3. Okay. Actually, was it bigger than or equal to 3? Yeah, it was bigger than or equal to 3, sorry. So including that point there. So we're going to need to know what that point is. Looks like it's probably 1, but let's actually work it out. In fact, we did work it out when I was thinking through the graph in my head, so I did know that. But I'm going to need that point. It's going to be from that point. And then it's the values of x that make this true. So it's true for this value of x, which I think is probably 1, up to, but not including this value of x, which is 2. Let's just verify algebraically that 1 minus 2 on x minus 2 is equal to 3. So let's subtract 1 and multiply both sides by -1, divide by 2. Okay, so it's going to be that, which means we've got 1 equals negative x plus 2, subtracting 2, sorry, it's -1. And so x indeed equals 1. Okay, so that's just giving me that value there. Okay, when x equals 1, y equals 3. And then if x is anything between 1 and up to, but not including 2, then the y value will be bigger than 3. Okay, so therefore that's what I want. So from the graph, use your graphs. A lot of my students don't look at their graphs anywhere near enough. They don't draw graphs enough. Here you had to draw the graph. It's sitting right there in front of you. Use it. From the graph, we know that 1 minus 2 of x minus 2 is bigger than or equal to 3 when x is bigger than or equal to 1, but less than 2. Okay, because the graph's not actually defined at 2, so therefore it won't be bigger than or equal to 3. It will just be undefined if we include 2 in that domain. Okay, let's have a look at question 5. Let f be a quadratic function, x squared minus 4 with domain R. G is another quadratic function, 4 times x minus 1 all squared minus 4, also with domain R. So no restricted domains, 2 parabolas. This is a parabola translated down by 4, that's f of x, and g of x is a parabola translated to the right 1 and down 4, so turning point at 1, 4, and a bit of a dilation there as well. Okay, the graphs of f and g have a common horizontal axis intercept at 2, 0. So that's telling us both f of x and g of x have an axis intercept at 2, 0. Find the coordinates of the other horizontal axis intercept of the graph of g. Okay, so we want to find the coordinates of the horizontal axis intercept, i.e. x-intercept, of the graph of g. So to find x-intercepts, we let y equal 0. So we're going to point G. So it's this one we're interested in. Okay, we add 4. We divide by 4. A number of my students expanded this bracket. It's not at all helpful to do that. You can, you'll get there in the long run, but there's no need to expand. You're making more x's in the equation. You've got x just sitting here. Simply do the same thing to both sides until you have x on its own. So it's x minus 1 squared, sorry. Square root of both sides. Square root of 1 is positive or negative 1. And so that means that x equals, we'll add 1. 1 plus or minus 1. Now 1 minus 1 is 0, and 1 plus 1 is 2. So there's two axis intercepts, one at 0, 0, and one at 2, 0. We already know about the common one at 2, 0, and so therefore the other axis intercept, which is what it asks us for, is 0, 0. Now, I didn't need to sub these in to find the y-coordinate. A couple of my students did that. You already know what the y-coordinate is. The y-coordinate is 0. You found these x values by letting y equal 0 at the beginning. Okay, you already know it's a horizontal axis intercept, so an x-intercept, which means the y value is 0. 2 marks there. Again, this would probably be a method for something. It may be somewhere along the way here. It may be just for solving g equal to 0. It may be for getting these two solutions by solving this. So it might sort of be almost a show that we're looking for. And then obviously there'd be an answer mark for stating the one set of coordinates that are the other axis intercept. I had a number of students give both intercepts. It's really important that you answer the question, which was to find the coordinates of the other horizontal axis intercept, so being clear that you're identifying which one is the answer to this particular question. Let the graph of H be a transformation of the graph of F, where transformations have been applied in the following order. So a dilation by a factor of a half from the vertical axis, parallel to the horizontal axis, so that's going to change the x coordinates. That's going to be a dilation in this direction, okay? And a translation by 2 units to the right, that is in the direction of the positive horizontal axis. Okay, so a couple of ways we could do this. Most of my students who tried to do it just by applying the transformations individually to the function did so incorrectly. I would strongly recommend a sort of first principles method here as a more reliable method if you are not very good at these. So let's start by thinking about what happens to every point on a graph if we do these two transformations. So if we dilate by a factor of a half from the vertical axis, we just discussed that that means we're stretching in this direction, so it's the x coordinate that's changing. We're multiplying the x coordinates by a half. And then we're translating 2 units to the right, so we're taking the existing x coordinate, which is half x, and we're adding a further 2 onto it to get to our final image point. Okay, so this is the image of x is half x plus 2, x dash that is half x plus 2, the image of x, and the image of y is unchanged, it's still just y. If I want to apply those transformations to a function, I need to make x and y the subject, not x and y dash. So rearranging this first equation, sorry, not x dash and y dash, we want x and y. So the x equation, if we make x the subject there, we're going to subtract 2 and then multiply by 2. And that's going to give us, you might either have it written this way, or you might expand it out and have it written this way, either way. Obviously y is just y dash. Okay, so that means if we want to transform f of x, y equals f of x is going to become, sorry, I lost my dashes in there, didn't I? Is going to become y dash equals f of 2x dash minus 4. Okay, and so we do that then. So that means that, what's this function called? H. H of x is f of 2x minus 4. And so that means it's going to be 2x minus 4 all squared, take away 4. Now, depending on how you did it and how you wrote it out, you might have had slight variations of that. You might still have had this factorized in here, which is fine. That's also correct. You could then expand out that 2. So 2 squared is 4. So it would be 4 times x minus 2 all squared, take away 4. Okay. But either way, and however way you ended up writing it, we're going to have h of x is one of these things. You could obviously also expand it out, but that's really unnecessary and taking a whole lot of steps that we just don't need to do, and therefore adding in additional steps where you could make mistakes. Alright, so there's 2 parts to this question. The first was to state the rule of h, which we've just done, and the coordinates of the horizontal axis intercepts of the graph of h. Now, This question would just be 2 answer marks. So you're going to get an answer for getting to that, and there's obviously you could do it with a lot less algebra written down. We'll have a look at that in a second. So just for that answer. And then the second is going to be an answer mark again for the coordinates of the axis intercepts. Now again, they're not going to be consequential based on your h, and that's because there are a number of different ways that you could have found them, and you could find them simply by applying those transformations to the 2 x-intercepts of the original graph. Okay, so f of x clearly has x-intercepts at negative 2, 0 and 2, 0, and so if you dilate both of those by half from the y-axis, they're going to become negative 1, 0 and 1, 0. And then if you translate them both to the right by 2, this one's going to become positive 1, 0, and this one's going to become positive 3, 0. So because you didn't actually need to find h of x in order to answer the second part of the question, those answers could have been obtained independently. That mark's not going to be consequential on your h. Okay, so it's going to be 1, 0 and 3, 0. Let's verify that if we solved one of these equal to 0, we would get the same values. So x-intercepts, whichever version of this you prefer. Maybe let's go with the original one, 2x minus 4 all squared, take away 4. So we add 4. We take the square root, so we get plus or minus 2. We add 4, so, 2x is 4 plus or minus 2, which means it's either 2 or 6. Sorry, that shouldn't be a comma. And therefore x is going to be dividing those by 2, 1 or 3. And so therefore they are 1, 0. It asks for coordinates, or 3, 0. Okay, so again, that's just going to be an answer mark there. So if they're not correct, then you're not going to earn anything. If you just want to apply the transformations to the function directly, you can, and some of you have good enough algebra to do that. A lot of you don't, and therefore I would recommend the first process. If we do a dilation by a factor of a half from the vertical axis, that is f of 2x. Okay, so dilation by half from the y-axis, f of x becomes f of 2x. Then if we translate 2 units to the right, so if we have a function g of x and we translate it 2 units to the right, it becomes g of x minus 2. Okay. Now what that means is wherever there is an x in your function, you replace it with x minus 2. So wherever there's an x, we replace it with x minus 2. So this becomes f of 2 times x minus 2. Okay, lots of students just stuck minus 2 in here, but that's not actually doing the transformations in the right order. Okay, so therefore if you're not very good at doing that reliably with your function notation, take the time to do this. I know this seems like a lot of work, but it actually really isn't. It's a very simple linear algebra, just rearranging little linear expressions, and it is much more reliable in terms of, you know, getting the answers correct. And obviously from this point you'd then get the same answer we got over there. Okay, question 6, the probability. I also found this was quite poorly done in the papers I marked recently. An online shopping site sells boxes of donuts. A box contains 20 donuts. There are only 4 types of donuts in the box. They are glazed with custard, glazed with no custard, not glazed with custard, not glazed with no custard. It's known that in the box, half of the donuts are with custard, 7/10 are not glazed, 1/10 of the donuts are glazed with custard. Okay, so this screams at me to set up a Carnell map or a two-way table because the donuts can either be glazed or not glazed and either have custard or not custard. So let's have glazed and not glazed donuts on one side of the table and custard and not custard donuts on the other side of the table. All the information is given to us as probabilities. So we can do 2 things here. We can either make the total of the table 1 and put probabilities in all of the boxes, or we know that there are 20 donuts, so alternatively we could make this 20 and fill it in with numbers of donuts. Okay, so whichever way is fine, you'll still be able to get the same answers. I might do it both ways. Let's start with the probabilities because that's how we've been given the information, so that's a bit easier. Half of the donuts are with custard, so the probability that a donut is with custard is a half. That goes down here. 7/10 of the donuts are not glazed, so not glazed total is 7/10. 1/10 of the donuts are glazed with custard, so glazed and custard is 1/10, so that's this up here. Okay, then we've got all the information we need to fill in the rest of the table. So focusing along the bottom here, first of all, those 2 values have to add up to 1, so therefore we're going to have half in here. Having a look at here, those 2 values have to also add up to 1. And so therefore this will be 3/10 here. Okay, then we can look at here. Those 2 values need to add to 3/10. and so therefore this will be 2/10, which does simplify to 1/5. Then either way, we can have a look at this way down. Oh, sorry, wrong pen. Let's try that again. This down here, they have to add to 1/2. That column has to add to 1/2. So these two values have to add to 1/2. 1/2 is 5/10, and so therefore there's going to need to be 4/10 in here, which is 2/5. Okay. And then looking across this way, these two things have to add to 7/10. 4/10 plus 3/10 will give me 7/10, and 3/10 is a simplified fraction. Okay, so we've got the table filled in. If you'd put 20 here, you would have then been able to work out all the values as number of donuts. So for example, half of the donuts are with custard. That would have meant this was 10, this was 10 here. 7/10 of the donuts are not glazed. 7/10 is 14/20. So that would be 14 here, which would mean that this would be 6 here, etc., etc., etc. And then 1/10 of the donuts are glazed with custard, so that's 2/20. So it'd be 2 donuts here. They have to add to 6, so that's 4. These have to add to 10, so that's 6. Horizontally here, they have to add to 14, so that's 8, and everything works out. So you could do it with whole numbers or with probabilities, either way. You don't have to simplify the fractions in the table, but you need to make sure that your answers to any questions are simplified fractions, and that proved an issue for a number of the papers I marked recently. A donut is chosen at random from the box. Find the probability that it is not glazed with custard. So that is probability of not glazed and custard. Okay, so not glazed and custard is here, which is 4/10, which, as I noted as I filled out the table, simplifies to 2/5. Now you could give that as 0.4, that's an exact decimal, or 2/5, but you can't give your answer as 4/10. It needs to be simplified. Okay, so one answer mark there, just for the one mark. The 20 donuts in the box are randomly allocated to 2 new boxes, box A and box B. Each new box contains 10 donuts. One of the 2 new boxes is chosen at random, and then a donut from that box is chosen at random. Okay, so the way that this is structured is there's sequence to this that's important. So what screams out at me here is I'm going to need to think about a tree diagram to help me. So we know that G is the number of glazed donuts in box A. Okay, so let's think about what's happening here. So we're going to have 2 choices here. We're going to, first of all, choose a box. One of the 2 new boxes is chosen at random, and then a donut is chosen, okay? And we're not interested in custard anymore in this problem. We're only interested in glazed. So forget about custard. That was just for part A. So we're either going to choose box A, or we're going to choose box B. Now it says we randomly choose a box, and there's 2 to choose from, so therefore there's a 50-50 chance. Okay, so then we've got box A, we could choose a glazed donut or not a glazed donut. And box B, we could choose a glazed donut or not a glazed donut. Okay, so we know box A, sorry, the 20 donuts are randomly allocated to the 2 new boxes, and each box contains 10 donuts. So box A has 10 donuts in it, and box B also has 10 donuts in it. All right, we already know from the information we've got here about that 7/10 of the donuts are not glazed, which means that 3/10 of the donuts are glazed, which means particularly if we filled out our table up here with numbers, we know that 6 of the donuts are glazed. Now it's the same donuts that we're redistributing across box A and box B, so that hasn't changed, okay? So we know that there are 6 glazed donuts. There are 6 glazed donuts. Okay, so mathematically, I could have written that as the number of glazed is 6. Sorry, that's a G. Number of glazed is 6. Okay. So we've got 6 glazed donuts, and that doesn't change. We know there are G glazed donuts in box A. Okay, that's what this tells us. G is the number of glazed donuts in box A. So there are G glazed donuts in box A, which means that there must be 6 minus G glazed donuts in box B. Okay, so let's think about that then. If I choose box A, so now I'm looking at my tree diagram and I'm looking first of all at these 2 things. If I choose box A, the probability that I choose a glazed donut out of box A, there are G glazed donuts in box A, out of the 10 donuts in the box, okay? Which means that there is 10 minus g non-glazed donuts out of the 10 donuts in the box. In box B, I've just worked out that there are 6 minus g glazed donuts. So there are 6 minus g out of the 10 glazed donuts in box B. And that means I could work out this expression here by doing 1 minus 6 minus g over 10. But actually, I don't think I need that number to work out the answer to the specific question I'm being asked, or not number, that expression. So I'm going to ignore that one. This one's actually the one that's important here. That's actually what we need. So you might have just focused on that one and not worried about the whole rest of the tree diagram. So we want to find the probability in terms of g that the donut comes from box B given that it is glazed. So we want the probability of box B given that it's a glazed donut. Okay. So therefore we're going to need the probability of the donut being from box B and glazed over the probability of it being glazed. Okay, so we already know the probability of it being glazed. It's 6 out of 20, which is 3/10, okay, because we've got 6 glazed donuts all up. Probability of it coming from box B and being glazed is about us focusing on this branch, a half times 6 minus g over 10. A number of students didn't multiply it by a half. A number of students just talked about 6 minus g and they weren't looking at a probability, okay. So on the numerator here, we're going to have half times 6 minus g over 10 divided by the probability of g, which we already know is 6 on 10 or 3/10. Sorry, 6 on 20 or 3/10. Okay, so we've got fractions in fractions here. Let's just split it out. So on the numerator there, I've got 6 minus g on 20, and then I'm dividing that by 3/10, which means I've got 6 minus g on 20 multiplied by 10 on 3. So the 10 and the 20 will cancel down. So that's going to be 1 and that's going to be 2. And so I've got 6 minus g on 6 is my final answer to the question. So I awarded an answer mark here, obviously, for the final answer needs to be correct. And then I also awarded an answer mark for thinking through that value there, which is probability of g given box B. Okay. Or I guess, depending on how people wrote it, getting to this expression as the probability of g and box B is also relevant as well. Okay, so 2 marks there. That was quite tough. I found a lot of students struggled with that one. The online shopping site has over 1 million visitors per day. It's known that half of these visitors are less than 25 years old. Let p hat be the random variable representing the proportion of visitors who are less than 25 years old in a random sample of 5 visitors. Okay, so p hat is a proportion, which means that p hat can't be binomially distributed, because binomial distribution is for a discrete random variable, and p hat is a proportion, not a number of. Okay, so we need to define a new variable. This is the thing I find students have real trouble with. You can't use the binomial distribution for p hat. You need to define a new variable, which isn't the proportion of visitors, it's the number of visitors. Okay, so we're going to let x equal the number of visitors who are less than 25 years old, because that is a discrete random variable. Okay, and x is therefore can be distributed binomially, where n is the sample of 5 visitors, so n is 5, and p is the probability that a visitor is less than 25 years old, which we're told is half. Okay, so that's important. That's my first mark. It'd probably technically be a method, but it's essentially going to be the same. You have to define your variable and how it's distributed. Okay. Then I need to recognize that what I'm trying to work out is, also what I understand from this is that if p hat is the proportion of the number of visitors, that means that p hat is the number of visitors out of 5. Okay. And so that therefore means that x is 5 times p hat. The question we're being asked is to find the probability that p hat is bigger than or equal to 0.8. We need to then relate that to x so we can use our binomial distribution. So that is the probability that x is bigger than or equal to 0.8 times 5, which is probability that x is bigger than or equal to 4. Okay, then we know that x being bigger than or equal to 4 is either x equals 4 or x equals 5. And binomial distribution we can use, so probability x equals 4 is 5 choose 4, 1/2 to the power of 4, 1/2 to the power of 1, which is n minus x, so 5 minus 4, plus probability x equals 5 is 5 choose 5, 1/2 to the power of 5, times 1/2 to the power of 5 minus 5, which is 0. Okay, 5 choose 4 is 5. Then we've got 1/2 to the power of 4 times 1/2, plus 5 choose 5 is 1 times 1/2 to the power of 5. So what I recognised here is that 1/2 to the 4 times 1/2 is 1/2 to the 5. So what you've got there is 5 times 1/2 to the power of 5 plus 1 times 1/2 to the power of 5. And so you actually have 6 lots of 1/2 to the power of 5. 1/2 to the power of 5 is 1 to the 5 is 5, and 2 to the 5 is 32. So we've got 1 on 32, 6 times 1 on 32, so that is 6 on 32, which is not a simplified fraction, and so 3 on 16 is my final answer. If you worked with decimals there, your exact answer should have been 0.1875, but can I strongly recommend working with fractions over decimals? You would have done a lot of long multiplication to work out what 0.5 to the power of 5 is, whereas 1/2 to the power of 5 is really just 1 to the power of 5 and 2 to the power of 5. So when you work with fractions, you're actually able to work with whole numbers when you're raising them to a power, and so it's actually much easier mathematically. So my instinct would be to always use fractions over decimals when I'm working by hand. Okay, so I'm definitely going to get an answer mark for that final answer at the end there. That would be my third of the 3 marks. As I said, a method for setting up your binomial distribution and defining a new variable, which you need to do. And then I had my next method here was for recognising that the probability that x is bigger than or equal to 0.8 is the probability that x is bigger than or equal to 4, but I did require students need to recognise that x bigger than or equal to 4 required them to work out 2 different probabilities, x equals 4 and x equals 5. Lots of students wrote this, but then just worked out x equal to 4, and so I felt that hadn't got far enough along yet to earn the second mark there. As I said, I didn't mark this exam, so I'm speculating as to where the marks might have been allocated. They could have been allocated differently by VCAA in 2021. But I have marked before, and I'm hazarding my best guess, but you never know, could be slightly different. Okay, question 7. A random variable x has the probability density function f, given by, it's a piecewise or hybrid function, but given that it's this and 0 everywhere else, you can really just think about f of x as being that. It doesn't actually need to be defined as a piecewise function. K is a positive real number. Show that k is equal to 2. Okay, so show that means that we forget that we've ever been told that k equals 2. We read this question as find the value of k. Okay, and because we're showing that, we really need to be quite explicit about what we're doing. Now, the way we're going to be able to find k is because we know that this is a probability density function, and so therefore we know that the total area under this function has to be 1, and so we're going to start with that. So we therefore know that the integral from 1 to 2, which is the domain of the function, which is k on x squared, that has to equal 1. Okay, so in order to anti-differentiate this, I'm going to be thinking of this as being kx to the negative 2. Now you could take that k out of the integral if you want, you could divide it over the other side if you want, you could do lots of different things with where you sit the k. I'm just going to leave it there. It doesn't help me hugely to take it out, but you might like to. Okay, so anti-differentiating x to the negative 2, we add 1 to the power, which takes us to negative 1, and we divide by that new power. So we're going to have, don't forget my k, sorry, kx to the negative 1 dividing by negative 1. And before I go substituting anything into that, I'm going to think about what this actually means. So x to the negative 1 means that's on the denominator of the fraction. So actually this is negative k on x from 1 to 2. Okay, so now we're going to sub in 2. So we're going to have negative k on 2 minus, we're subbing in 1, negative k on 1. And that has to equal 1. So we've got negative k on 2 minus minus plus k. Negative half of k plus 1k is positive half of k, and so therefore k equals 2. All right, so we have shown that. So the 1 mark there is going to be for a clear process. You would obviously need to start here, but that's not where you earn the mark. We need to see the process of you getting from that integral to k equals 2. Okay, so it's a method mark for showing. Be more explicit than you would normally be when you're showing something. Write all the steps so it's really clear how you've progressed from the beginning to the end of the answer. Find the expected value of x. Okay, so expected value of x is the antiderivative of x times our function. And we now know that k is 2. And we knew it even if we couldn't answer part A because we were told it. It's the antiderivative of x times your function over the domain of your function, so 1 to 2. Okay, so simplifying this expression before you go anti-differentiating it, if you have x times 2 on x squared, you therefore have 2 on x. When we anti-differentiate 2 on x, we get 2 times log e of x. You might be referencing your formula sheet for a couple of things here. First of all, expected value of x for a continuous random variable. That's it there. Mean. So you obviously have to know that expected value of x is mean. Okay. And we do x times our function. Obviously, negative infinity to infinity only applies if your function's actually defined over that total domain. Otherwise, you're using the endpoints of your domain to integrate. The second thing, we just integrated essentially 1 on x. And so we've got that here. So antiderivative of 1 on x is log e of x. And so therefore, the antiderivative of 2 on x is going to be 2 times log e of x. It's obviously where x is bigger than 0, but I think we've got that from memory. Oh no, we haven't. We're about to substitute things in, but we're going to substitute in numbers that are bigger than 0 anyway, so that's fine. Otherwise, you would use the modulus of x, but it's not actually relevant in this problem. 2 times log e of x from 1 to 2. We're going to substitute in 2, so that gives us 2 times log e of 2, and subtract and substitute 1, 2 times log e of 1. Log e of 1 is just 0, so that whole second part there is just 0, so we get 2 times log e of 2. If you want, you can think about that 2 going up into the power, so this is the same as log e of 4. There is no need to do that though. You've answered the question here at this point, so either of those is correct. The first mark would be for a method for knowing that you need to do the integral from 1 to 2 of x times your function. Okay, gradient of a function, question 8. The gradient of a function is given by dy dx equals the graph of the function has a single stationary point at 329 on 4. Find the rule of the function. Okay, so to find the rule from the derivative, we're going to need to anti-differentiate, and then we've got a point that we can use to find c. Before I anti-differentiate, I'm going to just rewrite that square root as being x plus 6 to the power of a half minus x on 2 minus 3 on 2. Okay, the rule for the function, it's not called f of x. The derivative is called dy dx, so therefore the antiderivative will be y. So y is going to be the antiderivative of our function. Sorry, antiderivative of our derivative with respect to x. Okay, again, formula sheet if you need. Antiderivative of ax plus b to the n, sorry, the eraser there, is this one here. Okay, so in our problem, we're anti-differentiating x plus 6 to the half. So a is 1, b is 6, and n is a half. And we can use our rule here to do that. So make sure you know what's there and you can use it. So we're going to add 1 to the power, which makes it 3 on 2. We're dividing by that power. We're also dividing by a, but a is 1. Okay, so we're doing 1 divided by 3 on 2. And that's going to be x plus 6 to the power of 3 on 2. Minus x on 2, we just add 1 to the power, divide by the power. So instead of being x to the 1, it becomes x squared, and we're dividing by 2, so that means we're going to get 4 on the denominator of that fraction. I had a number of students have trouble with that at this instance, so if x on 2, and then you want to divide by 2 again, which means you're timesing by a half, and so that 2 goes into the denominator. That's how you get 4. Alright, and then 3 on 2 is just a constant, so when we anti-differentiate it'll become 3 on 2x, and then plus c. The point is going to be needed to find c. Alright, let's just tidy this up slightly. So 2/3, 1 divided by 3 on 2 is 2/3. X plus 6 to the power of 3 on 2 minus x squared on 4 minus plus 3x on 2 plus c. Okay, so now we need to sub in our point. Okay, when x equals 3, y equals 29 on 4. Okay, so we're going to substitute the point 3, 29 on 4. And when we do that, we're going to get 29 on 4 equals 2/3 times 3 plus 6, which is 9 to the power of 3 on 2, minus, that's going to be 9 on 4, and minus 3 times 3 is 9 on 2 plus c. We want to solve this for c. So power of 3 on 2, if you've got something to the 9 to the power of 3 on 2, or anything to the power of 3 on 2, you've got two powers in one there. You're recognizing that 3 on 2 is a half times 3. And so we can just focus on those powers separately. Take the square root of 9, which is the power of a half, and then cube it, which is 27. Okay. So we're going to have 2/3 times 27 minus 9 on 4. Now I've got 29 on 4 on the left-hand side and 9 on 4. So I'm going to write everything over 4. So 9 on 2 is 18 on 4. I'm going to need to collect some like terms at some point. So 2/3 times 27, 1/3 of 27 is 9, so therefore 2/3 of 27 is 18. Again, you shouldn't need to get to 54 on 3. Try and think through what that means. If you know what a third of it is, you're dividing 27 by 3 and then timesing by 2, rather than timesing by 2 and then dividing by 3. And then we've got minus 9 on 4 minus 18 on 4, so that's minus 27 on 4, and plus c, and that's all equal to 29 on 4. Okay, I'm just going to get rid of some of my scribbles over here so I've got room to keep working. Could have used a little more space in this question, and most of the students found that as well. Okay, so C is going to be 29 on 4. We're going to add 27 on 4 to that, and then we're going to need to take away 18. 29 on 4 plus 27 on 4, what's that? 36 plus 20, 56 on 4. And 4 goes into 56 14 times, so that's 14 minus 18, and so minus 4. So C is negative 4, and so therefore the rule of the function is 2/3 x plus 6 to the 3 on 2 minus x squared on 4 minus 3x on 2, and then minus 4. Okay, so 3 marks there. I actually awarded them, and it may not be how it was done, I awarded them one for anti-differentiating that part of the function correctly, the other for anti-differentiating these two bits of the function correctly, and then one for the final answer here, which includes obviously getting to the negative 4, c equals negative 4. It may have been the case that the marks would have been for method, knowing that you needed to anti-differentiate. Even if it wasn't perfectly correct, you could have earned that if it was clear that you were attempting to anti-differentiate. It could have been method for knowing that you then needed to substitute the point in to find C, and then a final answer here at the end. Yeah, hard to know. Determine the nature of the stationary point. Okay, so we already know that it's a stationary point, so it's not about showing that it's a stationary point. It's not what it's asking you to do. We also know that it's the only stationary point. So there are two ways to determine the nature of the stationary point. I prefer to use a sign diagram because second derivative isn't really part of the Maths Methods course, but those of you who are also specialist students who are familiar with the second derivative, you can use the second derivative. But I'm just going to be using a sign diagram, and a sign diagram requires us to think about the value of the gradient either side of the stationary point. So we want to set up a table where we look at 3x values, the stationary point itself, and then a point either side of it. We want to evaluate the derivative or gradient at those 3x values, and then we want to interpret what that means for the shape of our graph. Okay, or you might write slope or something like that there in that last part. Okay, so we should be able to do part B even if we couldn't do part A, because we don't actually need the function, we just need to use the gradient, dy dx, which we were given right at the beginning. Alright, we know there's a stationary point when x equals 3, and we should be able to verify that by thinking about when we substitute 3 into the derivative. Okay, if we do that, we would get root 9 minus 3 on 2 minus 3 on 2, which would be 3 minus, taking away 3 on 2 twice is taking away 3, and so that is indeed 0. Okay, so the gradient at 3 is 0, but we were told that, so we can pretty much just pop a 0 in here. Oops, sorry. Then we want to think about a point either side. Now, I'm just going to write my derivative down here so that we've got it. We know that it is x plus 6 minus, was it x on 2? I'll go up and check it in a minute. Minus x on 2 minus 3 on 2? Yeah. Okay, so I want to be able to substitute a value either side here. Now, I want to make life easy for myself. I know it's the only stationary point, so I don't need to worry about staying close to this stationary point. If there were multiple stationary points, so let's say we know we've got, a stationary point at 3 and 29 on 4, okay? But if there were other stationary points, I need to be careful that if I substitute in an x value over here, then that might indicate that the gradient before the stationary point is negative, whereas actually right before the stationary point, it's a positive gradient. Right after the stationary point, I want to get negative gradient. So I would try to stay with values quite close to the stationary point, but the fact that the question tells me that it's the only stationary point means the graph never turns around again, okay? So I can pick any value to the left of 3 and any value to the right of 3, and that should tell me about the gradient for all values on either side, okay? So therefore, I'm going to be strategic about the numbers that I use. I don't want to stick 2 into here, because then I'm going to have root 8, and that's not very nice. I'm going to be needing to try and approximate what root 8 is in my head, and how does that compare to root 8 minus 1 minus 3 on 2, is that positive or negative? I'd rather be working with whole numbers where I can be really clear in my mind about whether it's positive or negative. So obviously 3 was a good number to stick in here because 3 plus 6 is 9 and root 9 is a whole number. So let me think about the numbers either side of that would also give me whole numbers. So obviously I can calculate root 4. So that would happen if x is negative 2. So let's use that as one of my values. And I can also, root 9 we've already thought about, so the next square number after that's 16. So if I put 10 in here, that's going to allow me to have root 16. So thinking a bit strategically about making this easy for myself, okay? So we're looking at when x equals negative 2, dy dx is going to be root 4 minus, so minus minus, so it'll be plus 2 on 2, so plus 1. And minus 3 on 2. Okay, so that's going to be 2 plus 1 minus 3 on 2. So that's 3 minus 3 on 2, which is 3 on 2, which is positive. And then when x equals 10, dy dx is the square root of 16 minus 10 on 2, so that's minus 5, and minus 3 on 2. So we've got 4 minus 5 minus 3 on 2, so it's negative 1 minus 3 on 2. Negative 1 minus 1.5 is negative 3.5. Oh, sorry, what am I saying? Negative 2.5, so that's negative 5 on 2. So it's clearly negative. So when x equals negative 2, the derivative is positive 3 on 2, so the graph is going to be sloping up. When x equals 3, the derivative is 0, so the shape is going to be flat. And when x equals 10, the derivative or the gradient is equal to negative 5 on 2, and so the graph is going to be sloping down. Okay, and so therefore, let's parrot the phrasing, determine the nature of the stationary point. The stationary point at x equals 3 is now stationary points are the stationary points of inflection, local minima or local maxima. So we might say that it's a local maximum. But in this case, because we know that it's the only stationary point, if a function only has one stationary point and that stationary point's a local maximum, it's therefore the absolute maximum. So we could actually just refer to it as the absolute maximum, or even just the maximum, I think would be okay. So be careful about how you phrase that sentence. Some students said things like x equals 3 is a maximum. That's not true. The point at x equals 3 is a local maximum. When x equals 3, the value of y is a maximum, but the question asks you to talk about the nature of the stationary point. So the stationary point at x equals 3, or you could even give the coordinates there. The stationary point at 329 on 4 is a local maximum. Okay. So obviously a mark for identifying or absolute would be okay as well. a mark for identifying the nature of the stationary point, and it's a 2-mark question, a mark for some evidence for that, okay, which would be a properly set out sign diagram. Now it's really important that your sign diagram doesn't just have plus and minus here, okay? That's not you actually calculate, you need to actually calculate values in the sign diagram so that there's verification of what's actually happening for this particular function. The other alternative would have been to work out the second derivative, whatever that was, sub x equals 3 into that, and then if you are looking for a maximum, you're looking for the second derivative to be, which way around are we looking for it? We're looking for it to be less than or equal to 0 in order for the, or less than 0, sorry. We're looking for it to be less than 0 in order for this to be a maximum turning point. Okay, so you're going to need to show that though. So actually calculate the second derivative, substitute x equals 3 into it, calculate a value, and therefore interpret that because that second derivative is less than 0 when x equals 3, you have a local maximum. Or in this case, because it's the only stationary point, an absolute maximum. Okay, question 9, last question on the paper. This was quite tough and, in my experience, very poorly done. Consider the unit circle, x squared plus y squared equals 1. Okay, so unit circle, centre at the origin, radius of 1, that information is shown in the diagram as well. And the tangent to the circle at the point P, shown in the diagram below. So the diagram indicates that the tangent is perpendicular to the radius, and that's actually true for all circles. It's a property of circles. But it's given to you clearly in the diagram. And we've got this point A at 2, 0. Show that the equation of the line that passes through the points A and P is given by this. Okay, so there are a number of different ways to do this. What you really wanted to notice here is that your circle has a radius of 1, and so therefore that means that this length here is going to be 1. You're given the coordinates of the point A, which means that this length here is 2. And then therefore you could use Pythagoras' theorem to show that this length here is root 3. Okay. Or you might not even have needed to use Pythagoras' theorem, because actually if you recognise that if you've got a right-angled triangle with the hypotenuse is 2 and the base length here is 1, that's our special triangle, and this is root 3, and therefore this is pi on 3, and therefore this is pi on 6, and all those sorts of things. So actually, straight away, if you recognised what was happening here, you recognised it as the special triangle, you automatically then knew that this angle in here was going to be, which one is that? Let me turn it around in my head. That's pi on 3 there, or this is pi on 6 here. Okay, there were a number of different ways you could get to that. You could obviously also use the trig. You could have used the, I don't know, some students used that without even working out the root 3. You could have used that sine of the angle OAP is opposite over hypotenuse, so that would be 1 over 2, and therefore from that you could work out that angle OAP is pi on 6, all sorts of things. Okay, so then there's a number of ways that this is useful in terms of actually working out what we need to show that the equation of the line that passes through the points AP is this, is we need to first of all show that the gradient is clearly negative 1 on root 3, and then we need to show that the equation is that. So a number of ways that we could do this. Obviously you've got a right-angled triangle here, and we know that the gradient of the line OP is equal to the tangent of that angle in there. And even if you hadn't worked out that angle, okay, so let's say we hadn't got that far, as I said, I saw lots of different quite good methods here. Let's say we call that angle theta. We know that the gradient of line OP is tan of theta, and we know that in this case, tan of theta, because we have a right-angled triangle, tan of theta is opposite over adjacent, and so that's root 3 over 1. And so we know that the gradient of OP is root 3, and so that means that the gradient of AP is, because they're perpendicular, negative 1 over the gradient of OP, and so it's negative 1 on root 3. Okay, so that would be one way that you could show that. The other way was to use the fact that just directly thinking about if you'd worked out these angles, so let me put those angles back in. If you knew that this was pi on 3 and this here down here was pi on 6, okay, so that means that that angle under there is pi on 6, or that that angle there is 5 pi on 6, okay. And so that means straight away, rather than working out using the tan to find the gradient of OP, you could instead have said that the gradient of AP is tan of, now it would either be negative pi on 6 using that angle under the x-axis, or tan of 5 pi on 6 using that angle above the x-axis there. But either way, that would again tell you that it's going to be negative 1 on root 3. Okay, so a method to find that. The other thing you could do, which I actually did the first time I did this, and actually it proved really useful when I got down to the last question on this page, is rather than think about that sort of right angled triangle OAP that's lying on its side, I then thought about a smaller right angled triangle in here. Once I'd used the bigger triangle to work out that that angle was pi on 3, I then used that smaller triangle, which I recognised. Let me just rub this bit out here. So let me put some letters on these so we know what we're talking about. So that's P there, and that's O there, and that's A there. If I focus on the smaller triangle, draw them so they're in the same orientation, that's O there, okay, and that's P up there, and then this is, let's call that something else. Let's call that X, for example. These are similar triangles because this angle here is also pi on 3, and it also has a right angle, and that's pi on 6 up there. So they're similar. And in the smaller triangle, we know that that is 1. And so therefore, if you think about scaling this down, this is just all the side lengths have been halved. And so this will be half, and this will be root 3 on 2. And so the advantage of that is what we actually get is the coordinates of the point P. So we now know that point P has coordinates of half root 3 on 2. And then from that you could have used rise over run to find your gradient. Root 3 on 2 divided by a half tells you your gradient of OP is root 3, and then the negative reciprocal of that gives you a gradient of AP. So lots of different ways to go about it, but actually, as I said, having thought through the coordinates of this point up here helped me later on in the question. So you would have had to have sort of thought that through at some point. Okay, so all I've done here is shown that the gradient is negative 1 on root 3. I've given you sort of 2 methods and talked through a third option there. And so either using, so at this point, I'm just going to say that I would have given a method for showing that the gradient is negative 1 on root 3. And then 2 different ways we can then come up with the equation. I use y minus y1 equals gradient times x minus x1, which means y minus, use your point 20. You could also use the point P you've just worked out, but that's much more complicated. Use A. So y minus the y coordinate of A equals the gradient times x minus the x coordinate of A. Sorry, I wrote 1 on root 2, that should be 1 on root 3. Just fix that. Okay, so that means that y equals, let's expand these brackets, negative 1 on root 3x plus 2 on root 3, which is what we were being asked to show. Let's just write it as that, which is exactly what we're being asked to show. Or you might have used y equals mx plus c, which is y equals negative 1 on root 3x plus c, then subbing in the point 20. And so c equals 2 on root 3, and so therefore y is negative x on root 3 plus 2 on root 3. Okay, so a number of students weren't clear enough about how they showed that the gradient was negative 1 on root 3, so they didn't get that first method, but they could earn the second method, which was having found the gradient, then showing that the equation was this by subbing in the point. That wasn't that well done. As I said, question 9, I found quite a lot of students didn't earn very many marks here, and even the best students sort of tended to, struggle a little bit here and not earn 8. Well, obviously not the very best, but, quite strong students. Okay, so then we've got a transformation. So we've got a transformation where Q is any real number except for 0. So the key thing here is to recognise what this transformation actually is. If you were to multiply that out, you're just going to have x and qy. Oops, sorry, qy. And so what you're seeing is any point xy becomes the point x qy. So we're multiplying all the y values by q, which means we're doing a dilation from the x-axis. Okay, so that's the transformation to think about. So, you can think graphically here, we're dilating this line AP from the x-axis. So that means that that x-intercept there isn't going to move anywhere. Okay. Hang on, let me just see what we're dilating. And let the graph of the function of h be the transformation of the line that passes through the points A and P under T. Yeah. So if you dilate from the x-axis, which is this way, that x-intercept there actually isn't going to change. So the line might become this, it might become this, it might become this, etc., etc. Okay, so let's go back and see what we're asking, what we're trying to find here. Find the values of Q for which the graph of H intersects with the unit circle at least once. Okay, so we know when we haven't done any dilation, the graph is just touching it exactly once. Okay, so that happens when Q, this is when Q is 1. We haven't dilated at all. Obviously, if we made Q bigger than 1, we would be stretching away from the x-axis. So we'd be doing this. Okay, and so that's not going to intersect at all with the circle. So we're going to need for Q to be, so that's if Q is bigger than 1. If Q is less than 1, okay, we're going to be intersecting in here. Now I'm just talking about positive, so that's if, now if Q were to equal 0, okay, we're going to end up with a horizontal line that intersects the graph twice, so that's okay. Then if Q were to be less than 0, negative, but only if Q were to be -1, that would be when we would exactly be tangential down there. So this here is when Q is between -1 and 0. Okay, this one here is when Q equals -1, and then obviously if Q is anything less than -1, we're not going to intersect the circle at all. So we're interested in the ones between here and here, which happens when Q is between -1 and 1. But actually we're given a definition for Q here, which tells us that Q can't be 0. It could be any real number except for 0. So actually we're not interested in that one there when Q equals 0. That's an issue. We don't want that one. We want everything else. So Q could be anything from -1 to 1. Except for 0. A couple of students got the -1 to 1 idea but didn't see the excluding 0 bit there. You could obviously also write that same information as -1 to 0, union 0 to 1. Okay, both of those, just different notations for the same thing. Okay, let the graph of H intersect the unit circle twice. Okay, so again, H being our transformed line that goes through A. Let the graph of H intersect the unit circle twice, so that's going to mean that it can't actually equal -1 or 1. Find the values of Q for which the coordinates of the points of intersection have only positive values. Okay, so let's go back here and think about this. Let me erase all of these red lines here. Okay, so we want to intersect twice, just by dilating from the y-axis. I'm actually going to get rid of all this other stuff as well. I'm going to put those coordinates of P back in there. That was half √3 on 2, because they're going to be useful. Okay, so we want to intersect twice. Let's just go back and check. Find the values of Q for which the coordinates of the points of intersection have only positive values. Okay, so we know that they intersect once when Q is 1, so that's not going to be an option. We know that they're going to intersect twice, okay, but we want them to have only positive values, so we don't want it to intersect at the y-axis here. So we want to think about the situation where it could intersect twice with 2 positive values, okay? Similarly here, obviously, that could happen down here where we do that sort of thing, okay? So what that means is the point where we intersect, or points where we intersect with the line have to both be positive. Okay, so that's only going to happen if this first point of intersection is to the right of P. Okay, so we know, for example, we know, for example, that when that first point of intersection is exactly when that first point of intersection is exactly at P, we only intersect once. So therefore we know we're going to have to dilate so that we're less than that, which means this is when Q equals 1. Okay, so if this line comes lower under here, oh sorry, I'm not drawing. We need it to only come lower to the point where, you know, it doesn't drop, it doesn't actually hit the y-axis. Well, it will hit the y-axis, but where it doesn't hit it at that point there, okay? So what that means is we need for Q to be such that that the x-coordinate of point P, wherever point P is, so point P being a point where that point P has to be somewhere between here and here. Otherwise, if we drop too low and it goes past here, so what we need is for this coordinate here, sorry, I'm not expressing myself very clearly here, this we need for Q to be such that the x coordinate of the point where they intersect is somewhere between 0 and 1/2, okay? So we need to find Q so that the x coordinate of P, okay, so that means we need Q, let me try and articulate that. We need Q such that the x coordinate of P is somewhere between, sorry, not equal to 0, is somewhere between 0 and 1/2. Okay, so when we thinking about the fact we've already worked out that Q is going to have to be less than 1. Okay, so when we therefore squash this down, we're going to be intersecting twice, but we need for this second one here to be only somewhere between 0 and 1/2. If it's not between 0 and 1/2, that will be because it's sort of gone up here, okay? And if it's further here, it will be here, okay? So we want to be careful. We want to make sure that we're thinking about that. And so if we know if P is at 1, 0, so what we actually want to work out, sorry, if we sort of work out this limiting value here, what would be the value of Q to make that happen? Sorry, not 1, 0, 0, 1. We know that if that were to happen, okay, sorry. So I've realized actually I've sort of confused myself here, and in the process I probably confused you. Okay, so let's understand that when Q is 1, that y-intercept there, we've got our equation of our tangent, is this C value here, which is 2 on root 3. Okay, so we know that that is 0, 2 on root 3, and we all know that because that was a show that. So even if we couldn't find the tangent, we know that bit there. So we know that if Q were to equal 1, then our tangent line is only going to touch the circle once, and that's not what we're interested in this part. So we're going to need for Q to be less than 1. We need for it to squash down. But we only need for it to squash down so that it doesn't actually get to the point of the tangent that I've drawn in here. We don't want it to reach the point where the y-intercept is at 0, 1, because then we won't have, actually, can we have that? We do want, sometimes if Q reaches the coordinates of the points of intersection have only positive values. Okay, so if we had, then we would have 2 points of intersection, which is what we want, but only one of them would have a positive value, so that's not what we want. So we're okay as long as Q is anything in between these two things. That's going to give us 2 intercepts, and both of them will be positive. So therefore, what we need to work out is what would be the dilation factor, remember we're dilating from the x-axis, to make this point at 2 root 3 to end up at the point 1, okay? So we know that that would be, if we were to dilate, okay, so we're going to need to squash in that way. If we were to dilate by root 3 on 2 from the x-axis, then if we multiplied that by root 3 on 2, we're going to end up here at 1, okay? So that's the biggest thing. So Q can't equal 1, but that's the biggest thing that Q could equal. And Q can't equal root 3 on 2, but that's the smallest thing that it could equal. So we've now got our range of values for Q, okay? Okay, so we know that if P is at its original place, half root 3 on 2, then Q equals 1, and we only have one point of intersection, which is not what we want, so it can't actually equal that. And we know that if P is at 0, 1, then Q has to equal root 3 on 2, okay? And that only gives us one positive point of intersection, so we can't actually equal that, but we want everything in between these two things, okay? And so therefore Q can be anything that is in between those two values, so in between root 3 on 2 and 1, but not equal to either of those things. Sorry, that was a slightly convoluted explanation. I got myself confused with this root 3 on 2 out here, where I knew that's what I was heading for. Hopefully you managed to work that out in the end. But I think that part is probably the trickiest part on the paper, just in terms of the thinking that you need to do there. These subsequent parts are a bit more straightforward. Students tended to get them wrong through not including enough information and basically not considering domain rather than not understanding what was going on. Whereas part B, part 2 was conceptually quite complicated to think through. But it's all about that graph. Look at the graph. Think about what you need it to happen. You're trying to do a dilation. You can't dilate it more than that. You have to dilate it a little bit, but not a lot, all those sorts of things. Okay, so part C, for Q between 0 and 1, not including 0, but including 1. Okay, so obviously we're not just looking at this situation. We're just looking at that bit there. Okay, so we're not interested in where we sort of reflect it. Okay, so essentially Q can't actually be 0. Let me erase all of this so we can see what we're doing here again. So we're not interested in the part where the line becomes horizontal, but we're interested in anything bigger than that, but only up to there. Okay, so we're not interested in anything out here. So we're simply interested in those when we're looking at the line AP through those particular angles. Okay, so let's go back. So that's what we know about Q. Let P dash be the point of intersection of the graph of H with the unit circle, where P dash is always the point of intersection that's closest to A, as shown in the diagram below. Let G be the function that gives the area of the triangle OAP dash in terms of theta. Okay, so now we want to think in terms of theta. So we want to be able to redefine things in terms of theta. We want to remember that this is a unit circle. So actually, P dash, the coordinates of P dash can be really easily explained in terms of theta. P dash is the x coordinate at an angle of theta in the unit circle. So that is cos of theta. And the y coordinate is sine of theta. Okay, so if we want to find a function that describes the area of this triangle, we're going to need half times base times height. We can clearly see that the base is 2. The height, let's not use a black pen because we're going to get lost in there. The height here is the y coordinate, sine theta. So therefore, we know that g of theta, in terms of theta, a lot of students got this wrong because they gave g of x, it needs to be g of theta, is going to be half times the base, which is 2, and times the height, which is sine of theta. And so therefore that is g of theta is sine of theta. Now, the next thing we need to be really careful here, which is another reason why students didn't earn full marks here, is we want to define the function g. So a function has two parts to it. A function needs a rule, which we've just worked out, and the domain. Now, if we don't give the domain, we assume it's the implied domain, which would be R in this case. But that's not the case. R can't be anything because we've already defined that we're only interested in the Q values where we can dilate right up until there, but not including there. Okay, so that means this angle, theta can't actually be 0 because if theta were equal to 0, that would be when Q is 0. Okay, so if theta equals 0 means Q equals 0, and so we can't include that point. But up here where Q equals 1, which is our maximum value of Q, okay, that happens when theta equals, and we need to actually work that out. Okay, so if we think about what's happening here, we already know that that value happens, Q equals 1 is the whole situation we've been looking at over here. Okay, we know that when Q equals 1, this is half root 3 on 2. And so therefore we've already worked out, we did that ages ago, we know that that angle there is pi on 3 at that situation. So we can't have the angle any bigger than pi on 3, because if this angle got any bigger than pi on 3, then we would be looking at a situation where p hat would be over here. Okay, so because it wouldn't be the point of intersection wouldn't be the closest point to A. Okay, so you actually it wouldn't actually work. A number of students talked about the fact that theta could be pi on 2. They simply, and that happened later on. If theta was pi on 2, then you'd be saying that p dash is there, and therefore, if you did that, that's actually p dash, not this point up here. Okay, so this is the problem here. You actually don't get the triangle that you're talking about. So p dash can only go as far to the point where it's actually going to be tangent. After that, then it won't be, if the angle's any bigger than that, then it won't be the closest point to A, and p dash has to be the closest point to A. So the biggest value you can have is pi on 3. Okay, so we need to define this function. It's going to have rule and domain. So g can't be 0, because that would be when q is 0, and it can be up to pi on 3, which would be the value that would make sure that p dash is actually p. Okay, so that's going to be our domain. And then our rule for g of theta, not g of x, is sine of theta. So mark for the rule, mark for the domain, so that the function is fully defined. Determine the maximum possible area of the triangle OAP. So g of theta is a rule that defines the area of the triangle OAP, sorry, p dash. And we've just established that it is sine, but only over the domain from 0 to pi on 3, not including 0. Okay, so this is y equals g of theta. And so therefore, maximum g occurs when theta equals pi on 3. Mark for that. Does feel like you kind of get penalised for that twice, but I think that would be an answer mark. So again, if you haven't thought through the domain at part 1, you're not going to get any of part 2 right here. So really, you sort of lose the last 3 marks if you didn't think through this domain at all. And that's what happened to most students. Maximum g occurs when theta is pi on 3, and so therefore max g is the maximum area, and it is at g of pi on 3, which is sine of pi on 3, which, if we know our exact values, is root 3 on 2. Or if we think through that we already know that it's when this is half root 3 on 2. That's going to give maximum area. And you can work out the area of that triangle in that way as well. So answer mark here for that one. So as I said, question 9 was definitely quite poorly done, and really most students in my experience got locked out of the last 3 marks when they didn't think about the domain here. Being careful at g of theta, a number of students also lost that mark even though they could think through the logic of what was happening here. As I said, I think this was sort of conceptually the most difficult thing to think through here, so lots of students didn't get that one. Lots of students got the idea of what was happening here but missed the exclusion of 0, so also didn't get that one. And for some, their show that wasn't sufficient. So it was actually quite common for students to get absolutely fewer than half of the marks here in question 9. But the rest of the paper, I thought this exam 1 was relatively straightforward. So, question 9, a genuine differentiator here at the end.